So today's job, I have a folder full of numeric trees, maybe about 30 or 40. I already have some code to read what's in there and pull out all the terminal IDs, all the species. Now what I need to do is retrieve the higher taxa of all these terminals. I'll probably work at about the family level. And I want to see the overlap between this data and a separate data set. Now I already have some code and I'm still thinking how to do this. So for the higher taxa, I think I'll use this script taxon table to get the higher taxa of all the species. Because this one that uses 2 databases, so it's quite comprehensive. What else? I need to add in the other dataset is a large DNA barcode dataset. I need to find that and read that, and then organize it hierarchically. So I'll probably go through each insect order, and then for each order go through each family, and then see what is the overlap. So essentially for each family I want to see how many species in the trees and how many species in the DNA barcodes. So it tells us where the major gaps are. So that's the job for today. No idea how. What could this be? Does need some new components creating for this. Okay, this looks fine. So copy these commands into separate. So this is a new project. Okay, we're in the correct folder. So here's the locations of ITIS taxonomic database, which is stored on the computer, and the NCBI taxonomic database. Gives a path and file name of these. Taxon of interest. Okay, here we go. So let's specify which taxon we're running. And here, so here's the taxon name, it's insects, or formula on insecta, and this is the number corresponding to that taxon in the NCBI taxonomic database. So give that in the node switch, and this is insecta is put into this variable, which is red here. Okay, so it's just, this should give us some kind of table. Every time you open a very big file, I recommend actually saving any text documents you have open, because often it will crash depending on how it's formatted, and then you lose your work. Okay, so let's have a look. Right, this is a hierarchy. This is a sort of nodal specification of a hierarchy, which is not exactly what I want. I want kind of lineages on full lineages. What else? Oh yes, and we have this. Okay, this is what I think we need. Okay, so this for each species, and we have a full lineage, because this is what we need. So how? We'll put a rather large file, unfortunately. Probably the names of this. Let's try and copy this file. Into our working directory for this other project. And let's take a look. So this should be a faster file. So let's grep for the faster delimiter. Yep, okay. So we have so this is sorted. This is dereplicated per species, so one sequence per species. So one DNA code one sequence for each of 145,000 species. So we're going to have to read this list of species into. So this script, this is what we're going to be working on. Let's close what we don't need. And so we're reading in now the taxonomic table on the file of DNA barcodes. But I'm going to show you the existing function of this. It's reading all these. So these are Newick. This is basically Newick trees. There's 39, and it's pulling out all the species of these. Currently got 16,000 species overall of those 39 trees. So I think we need to add first. Okay, so what we've got. So we're reading the two files which should be specified on the command line. Here we're going to open these files. Taxon table and then Newick on the faster file. Let's just stop this and you can see species IDs. This one happens to be, this one is it's called non-canonical IDs. These aren't exactly assigned to a taxonomic species, but more of a something else. It can be informal or more formal sort of entity. But for the current purpose, we're ignoring the non-canonical stuff and just going for this taxonomic species. We need to pull out the. We need this information. So we need the species, which is the first column, and pull out the family here. So let's just copy what. Okay. So here's a random Andrina. This is a bee. Some bee species. So we'll have a regular expression to pull out what we need. I need to pull out the family. It's conveniently actually has the name family before it. So we're looking for this means start of a line. So over here, then we have any character which is not a space, plus which is multiple. So we'll just pull out this string here. So we'll put our brackets around this to pull out this into a variable, and we want to pull out the whatever string is after the word family. So $1 that just means anything between the first set of parentheses and $2, anything between the second set of parentheses. So it's worth checking it's pulling out exactly what you want. Sometimes it's just something unexpected. Okay, so also make it a bit clearer. Okay, so for a line of the database, pull out the species name and the family. Insect families always end in IDAE. So this looks fine. Now we need to store these. Let's store these. I need to think a minute which way we will be querying this. Okay, first so we need the so we just use the species as the query with the hash key and put which family it belongs to. Okay, you don't need to see this now, so it should be okay. Okay, so we're storing which family each species belongs to. Yeah, just thinking I also want to do this separately for each order. So maybe I've also, I think I should also pull out the order. We'll sort that a bit later. I'm going to figure out what to do about that. But anyway, next we need to also be reading in the FASTA file. Which is the name is stored in one variable. And FASTA files always delimited with this character. Okay, so these are all the IDs in the FASTA file. Okay, so we've stored the taxonomic information, the FASTA IDs. We're reading all the trees, pulling out all the binomials. So it's just printing the details to screen, and we need to add some more items here. So yeah, I think I'll do this per order. So we need to read the orders. We need a taxonomic rank order into an object. Okay, notice a problem here. Okay, more than one problem. This character's being. This should end in an A. This one here. Okay, so this is a slight problem. Okay, so maybe we specify a character here. Okay, so it's fixed one problem. That's not as much as up. 2, 4, 6, 8. Yeah, we're missing only about 2/3 of what is expected, but yeah, I've got the main ones in. There's a few missing in here. There's about 30 insect orders. There's only about 20 here, but we do have the big 4 and some of the big ones anyway. I don't know why it's reading number 1 here. This is a bit odd. So let's see here. Okay, now there's something missing here. Yeah, so we're putting the keys of this hash into this array, not the contents. Okay, fine. So we'll look through each order, and then for each order we need a list of families which belong to that order. So how to do this? We could actually just put them into this object we already have. So this is one way I store objects belonging to something else within a hash. It is probably a more elegant way to do this. But this does work. Okay, so we're storing with this order hash key. We're just listing the families belonging to that order, tab separated. So this should list the families for each order. For instance, strip zip terror, related to beetles probably, has this list of families in that database. So it's one of the smaller insect orders, and you can see something bigger like the flies. These are all fly families here. Okay, so for each for each family, okay, we need to then loop through all families. It should be a local variable. This is also a tab, start and end. So we put all for the current order, it pulls out all the families belonging to that order, and these are all then listed in an array. So then we need to loop through each of these families. Just sort these alphabetically. have all the different folders. So it's not just aesthetic, but it's more repeatable actually. Otherwise, it's sort of randomizing. Okay, so for tricopter, these dragon caddisflies, these are all the families. Okay. So as I say, let's recap. The aim is to find the overlap of these two, taxonomic overlap of these two data sets. I should know what this is. This is a taxon table. In one is the second switch, which is the barcode alignment. And these are the list of trees. Okay, so for each family, I want to know what's in the colon alignment. So I have this is where we read the species, so I need to know what family this species belongs to, and that's stored in this object here. So we'll have a conditional. Let's check whether or not, and check exactly what we're retrieving and what we're not retrieving for each faster ID. I'll just call this an entry because there's different entities in there. So we've either successfully retrieved a family name for a faster entity, or we have not. Now I know there's a bunch of non-canonical stuff in there, so probably that won't be retrieved at all. So it's fine if there's a few thousand of those, as long as we're getting something like 50,000 are retrieved. I think I'll probably be testing this process on one particular insect family. So I'll just limit the screen output here. Okay, so we've retrieved family name for 71,000, which is about what I expect of the faster IDs. So this is working here. So I think we'll just count these because these are so this data set is actually quite well sorted to species. So I'm going to count. Just going to count number of species for each family in the fast. For now, I might look more precisely at overlap a bit later, but let's call this count go-ones for family. We'll only do this if it has actually stored, retrieved the family name for this. We'll just count these up, use two plus signs to increment each time that family is encountered in the faster file. So I've counted how many members of this family. Save this. Okay, so surprisingly some families have nothing for whatever reason. And here's an outlier here. There's a huge number of colon barcodes for this family. But yeah, this is what we want. So we've counted. So next we need to know the same or similar for the species. Okay, so species terminals and the file legends which are being read into here. This object here. So we will do the same. We'll retrieve the counts in the so we'll do the same thing. let's look through all the species found in the terminals of all the trees and try and retrieve the family of each. So for the inner trees, in the phylogenies we have about 16,000 of all the trees. Most of them we have retrieved the family name. I want to get this a bit more precise. I'll do that a bit at a later time, but for now that's okay. So we have the family, and we will count tree terminals for family. Okay, this might be our first glimpse of the output of this. Let's see. Yep, okay. So we have just printed out for the flies. So here's all the families found in the taxonomic database for flies. Here's how many species we have ACO1 for, and here's how many terminals in the bunch of trees. Now this doesn't say if these are the same species or not, but it roughly states the amount of data for each. We can peruse this and see if we've got any major discrepancies. So we have a fly family, which we have a lot of barcode data for, but only 3 terminals in our tree. So maybe we want to get a bit more phylogenetic data for this family. We have a family with quite a lot of DNA barcodes and a reasonable number of terminals in a tree. If you run them, it's save a lot of barcode data and still reasonable coverage in the trees, but maybe we want to get this a bit more. So And I'm just looking for one in, if you have any examples in the other direction. We have a lot of data in the tree terminals and not so much code1 barcodes, which I wouldn't, for the current purpose, I wouldn't bother with, because I like to have a. It's good to have a code1 for each member of each terminal of the insect phylogen. This gives a system for querying. And let's see one case here. Only 3 code1 sequences for this family, but quite a few terminals, which is a bit of a waste of time. Or maybe this has just been filtered too much. We need more phylogenetic coverage for this family here. Okay, so I think this is roughly job done. I would refine this a bit. There's a few things need refining, and I'll actually check if these not just counts, but are these actually exactly the same species or not. Okay, so I think, yep, job done, and until next time.